Hello everyone, we are Team 5DOF. Today we present the Power Independent Emergency Escape System for EV Thermal Runaway. Let's get started. We have structured our presentation into 5 main parts. We will begin with the introduction to the problem, followed by the system overview and its working principle. Finally, we will demonstrate the reliability of our design through verification and conclude with the expected effects. This is the reality of an EV fire. When thermal runaway occurs, the power is cut and the electronic doors fail to open. Currently, vehicles have manual release levers, but as you can see, they are often hidden and complex. In a panic situation filled with smoke and fire, finding and operating these non-intuitive mechanisms is nearly impossible. This delay can be fatal. Since electronic systems failed during a fire, our core objective was clear: to develop a power-independent, purely mechanical system. First, we verified that a simple physical pull on the cable unlocks the door, confirming that electricity is not required. We initially considered a mousetrap principle to generate the force. However, we rejected this mechanism because it was too vulnerable to vehicle vibrations, which could lead to accidental activation. Therefore, we refined this concept into a much more stable design, which I will present next. Here's the system overview. The mechanism operates as a simple chain reaction. Our system consists of 3 power-independent components working as a single chain. Step 1. Detection. The burn stick receives the pressure input. Step 2. Transmission. The module converts this input into a driving force. Step 3. Release. The electronic latch acts as an output, mechanically unlocking the door. From sensing the pressure to releasing the door, it all happens mechanically. Before our design, meet the key component, the burst disc. Think of it as mechanical fuse. It physically breaks to release pressure instantly. No sensors, no electricity needed. Let's look at how this mechanism actually moves in the pictures. It starts with a burst of energy. As the high pressure gas rushes in, it doesn't just break the disc, it instantly punches the piston forward. Now, watch how the lever reacts. The linear push rotates the lever, which physically pulls the bottom cable at the bottom. We are essentially translating raw explosion pressure into a precise mechanical trigger. And we didn't forget safety. Once the piston finishes its job, the remaining gas automatically escapes through this vent, neutralizing the system immediately. Next represent the mechanical execution phase. In the normal state, the slider acts as a stored energy reservoir with a compressed spring. When the trigger is activated, the lever drops and the slider is released. This creates a strong linear pulling force on the cable, which is directly connected to the door latch. Essentially, we are using a mechanical chain reaction to bypass electrical failure. To summarize the output stage, we focus on 3 features. First, direct force transfer. The cable transmits physical force directly to the mechanism with zero energy loss. Second, mechanical override. We mechanically disengage the latch, bypassing the need for electrical power. And third, immediate egress. The result is a fully released door ready for instant manual escape. This completes our safety chain from pressure detection to door opening. Now, putting it all together, this is our integrated system design. As you can see, the piston at the battery pack, the module in the door panel, and the latch are all physically connected via cables. This represents our final, fully mechanical solution for emergency safety. Now, let's move on to the spring module verification. To guarantee the latch opens, we preloaded the spring by 30 millimeters. As shown in the graph, this creates a massive 300 newtons of initial force and maintains over 100 newtons until the end. It has enough power to overcome any resistance. To verify reliability, we establish realistic assumptions under the harshest conditions. We apply conservative mass limits and high static friction coefficients to simulate the worst-case scenario. Moving to the top right, we calculated the total resistance torque by summing spring load, weight, and friction. The maximum resistance to overcome is 3.875 Newton meters. Based on this torque, the system requires 400.9 newtons to unlock. However, a hydraulic piston delivers a driving force of 628.3 newtons. This results in a safety margin of 1.57. This confirms that our system guarantees successful operation even in emergency situations. Now let's look at the expected effects. First is economic feasibility. We achieved a highly durable mechanical design at a much lower cost than electronic backups. As shown in the table, the total cost is just 200,000 won. This is reasonable investment for a life-saving device. Next is fail-safe automation. Traditional systems require manual operation, which often leads to errors during panic. Our system eliminates this risk. It reacts to thermal runaway and unlocks automatically without any user intervention. This guarantees zero human error and ensures an immediate escape. Finally, I would like to highlight the maintainability of our system. We focus on two key advantages. First is non-destructive operation. Unlike traditional methods that physically damage the door, our system uses an independent latch release. This ensures zero mechanical damage, allowing for an instant reset simply by moving the lever. Second is our modular packaging design. The entire mechanism is built as a single detachable unit. This enables easy component level replacement without disassembling the entire door, drastically reducing repair time and costs. This concludes our presentation. We are Team 5DOF. Thank you for your time and attention.